So we're going to talk about low inflow estuaries. So those are typically estuaries that get very little or no fresh water input, but still they behave as estuaries, and that's why they are considered estuaries. Again, going back to the definition, but you don't know until you see it. So these are what are called hypersaline, inverse, and thermal estuaries, and we'll make the distinction among these three types of different estuaries today. And some of these show what's called also stomach transitions, and we'll refer to them also today. And while we talk about all these, I want you to think about the systems around Florida, because many of the coastal embayments in Florida fall in this category, and they might show some of these characteristics that we don't know very well, because we don't have enough data to classify them or to understand them in this context. So think of them in the local context as we talk about them. So before we get there, we use some terminology, and we talk about hypersalinity. That it just means high salinity. Right? And what that means is that the estuary or the embayment is saltier than the ocean. That's what we'll refer to hypersalinity. That the embayment is saltier than the ocean, and that means that that hypersalinity can be due to salinity changes outside the estuary. That is, it could be that you have fresh water affecting the ocean waters, but not the estuary. But most commonly, it's due to evaporation inside the estuary, inside the embayment. Well, evaporation outside, but that affects more the estuary itself, because there's less volume inside the estuary, so evaporation will tend to concentrate salinity in the embayment. But you can also have hypersalinity in high latitudes due to freezing inside the enclosed system. So that's hypersalinity. And now what's an inverse system? An inverse system is that shows an inverse density gradient. And we refer to an inverse density gradient relative to what we think in a regular estuary, in which density increases seaward. In an inverse density gradient, it means that density decreases seaward. Density decreases seaward. So it means that the embayment waters are denser than the ambient. And this causes an inverse circulation, inverse estuarine circulation. So outflow near the bottom, inflow near the surface, which is a reverse estuarine circulation. Outflow near the bottom. So that's an inverse. So we'll see how not all hypersaline systems are inverse. And also we have a negative estuary. A negative estuary, which would be, I guess, synonymous of an inverse, because you have a negative balance of buoyancy flux to the estuary. So what that means is that the estuary is losing buoyancy. In a negative embayment or a negative estuary, it means that it's losing buoyancy. So it's becoming heavier. The water inside the embayment is heavier than the water outside. So this is often related to a net loss of water due to evaporation. Or in other words, a negative hydrological balance. Okay, so now that we have those definitions in place, we can illustrate what we mean in this diagram. So there are systems that fall in either of this category, or there are systems that behave in both of these ways at different times of the year. Which ways do we mean? Well, the way of a classical lagoon. Think of a subtropical system or a tropical system during dry season, in which the temperature outside the ocean is lower, outside on the ocean is lower than the temperature in the embayment. So the temperature increases in the embayment. Also the salinity increases. So this is a hypersaline system. But in this case, the temperature is controlling the density, and in this case, the water inside the basin is less dense than the density outside the embayment, and that will produce a classical estuarine circulation, near surface outflow, near bottom inflow. Okay? So we have a hypersaline situation there. But the density field is controlled by temperature. Then, later on a different system or same system later on in the summer, when evaporation is very intense, the water temperature inside the basin is hot, is really hot, so the temperature really increases a lot. But also the salinity increases quite a bit in such a way that now the salinity becomes the dominant influence in the density field, in such a way that the density inside the basin is greater than the density at the ocean. So in that case, you're going to get the inverse estuarine circulation, inflow at the surface, outflow at depth. Okay, so think of this situation as different systems, or as the same system that can change with season or with time of the year, or at different times of the year behaves differently. So these types of systems, the question for these types of systems is, how does the system reverse and when does it reverse? And it will ultimately depend on the longitudinal density gradient. And now this is also for systems for which the mean flow is driven by the density gradient. The drawback in many of these systems is that in many instances the mean flow is driven by what you think instead of the density fields. Think of Ponce de Leon Inlet or St. Augustine Inlet. By tides or by wind. So this approach is for systems that are driven by the density gradient. All right, so here's another way of looking at it, at the same situation. We have a classical embayment in which we have either heating or precipitation and freshwater input causing the salinity, the density inside the basin to be lower than outside the basin. This causes near surface outflow, near bottom inflow. The surface outflow, in terms of volume outflow, is greater than the volume inflow. So that causes a net volume from the embayment out to the ocean. And in the inverse case, you could have concentration of salinity inside the basin, or you can have denser water originating from cooling. So in this case, you have more volume flux coming into the basin than volume flux going out, again because of losses due to evaporation. So in this case, you have a net volume in. So if I were to ask you which of these two situations show a longer residence time, what would you say? Which one would you say would have the longer residence time? Which flushes more efficiently? In the classical system, you're adding water, right? You're adding water, and it creates the exchange. In the inverse system, you're losing water. So which one would flush more efficiently? Where you add water or where you remove water? Huh? Where you remove it? Why would you say that? Well, it is I guess you could answer either way, but why would you say where you take water you would have a more efficient flushing?
In order to keep the water level the same, you have to have more flux in it. So you get new water coming in.
Well, the same when you add water, right? Right? So where would you have more concentration? You can see it in salinity. Salinity gets more concentrated under what condition? The inverse condition. Salinity gets concentrated there. It's not flushed as efficiently. So you have that the water remains longer here, and it's allowed to concentrate salt. So we would say that in an inverse situation, excuse me, in an inverse situation, you have a lower residence time, a longer residence time. Oh boy, I'm having a hard time. Okay, so ultimately the circulation will be determined by the relative influence of temperature and salinity on the density gradient. And you can look at it with that temperature salinity diagram as shown here. And it's a very nice way of thinking about the different ways in which a system can behave. So what you have here is salinity in the x-axis. This would be where the horizontal salinity contrast between the ocean and the basin is 0. And this area would be where you have lower salinity inside the estuary, high salinity inside the estuary. So as we move in this direction, in this diagram, we're going from hyposaline, which is a classical estuary, to hypersaline, which is an inverse estuary. And as we move in the vertical axis, you have a hypothermal situation in which where you have a cold estuary, that is, the temperature outside the estuary is greater than the temperature inside the basin. And then here you have, as you go down, you have a hyperthermal estuary, that is, temperature is greater inside the estuary than in the ocean. So in this quadrant here, you're going to have a warm and hypersaline estuary. In this quadrant here, you'll have a warm and hyposaline estuary. So in this quadrant, for sure, you will have a classical estuary, right? And also in this quadrant, for sure, you will have a cold and hypersaline estuary, so you'll have for sure an inverse estuary. So in these two quadrants, you can have either. You see how? You're going to have a warm and saline hypersaline estuary, or a cold and hyposaline estuary. So if we look at the density differences between the estuary and the ocean, we can draw the delta rho isolines, and this green isoline would be the line where there's no horizontal density gradient. So everything on this diagram that falls above the green line will be an inverse estuary. We saw that it makes sense that in this quadrant you're going to have an inverse estuary because it's cold and hypersaline. And down here you're going to have a typical estuary because it's warm and low salinity relative to the ocean. Now notice here that part of these two quadrants will show inverse estuary conditions. In this case, you're going to have, this would be a regular estuary, even though it would be a hypersaline here. It's warm. So this is the instance, in this very small part of the parameter space, in this small part, that's where temperature will dominate the density field and will cause a positive density gradient. That is a typical estuary condition in this small part of the parameter space. Similarly, in this small part of the parameter space, you will have hyposaline conditions. That is, the salinity in the estuary will be lower than the salinity outside, but still it would be colder, and that will favor conditions for an inverse estuary. So this is a small part of the parameter space where you will have inverse estuary, a small part of the parameter space where you'll have a regular estuary. Right? So it makes sense that, again, in these two quadrants, you will have an inverse estuary here and a regular estuary here. You follow this argument? So you can go to Panama City, to St. Andrew Bay, and look at the horizontal salinity difference between the estuary and the ocean, and the horizontal temperature difference between the estuary and the ocean, and you can place a dot there. Or you can follow a seasonal progression in this space and see where it falls. And you can choose whatever your favorite system is. Again, it could be Ponce de Leon Inlet, the area of Ponce de Leon Inlet, or the Guanajuato-Matasas River. I'm going to use that example toward the end to show how it can reverse. It can move around this diagram quite a bit. So this diagram is useful to understand. So there it is. There are the two areas that I mentioned, the two fuzzy areas. And it's really a small range in values in this parameter space. This is, again, the small area where it's hypersaline but not inverse. It's a thermal estuary. And this would be a hypersaline but an inverse estuary, not a classical estuary. So it's a cold estuary that behaves as an inverse estuary up here, right? And look at the parameter space in which you'll have classical estuaries. So from this line and this line all the way to the right, you're going to have classical estuaries. So most coastal systems will fall in this parameter space, and also as you move to the right in this parameter space. A few of them will fall here in the inverse estuary, and even fewer in these two categories. All right. So there are systems up to now we talk about hypersaline but not inverse. There are systems that are next to upwelling coasts. Coastal systems where you have upwelling right outside. Can you think of an area of the world where this happens?
Chile.
Where?
Chile.
Yes, that's a good one. That's a good example.
West Coast.
Huh?
West Coast.
That's right, the West Coast. Where? In Oregon? Huh?
Could it be the upwelling like what Amy's talking about with the divided canyons? Could that?
Well, it has to be upwelling right next to the coast. So in such a way that you have colder water than the embayment. So cold water just outside. So it's preferential in the southwest. Actually up to north of San Francisco, there's a good example of this system, Tomales Bay. So all these basins will fall, in this parameter space, will fall down here. So they can be hypersaline inverse estuaries, they can be hypersaline but not inverse, and they can be classical estuaries. How is that? Well, when they're very long basins, they will fall here because they will be practically disconnected from the cold water. So they will become hypersaline, and that salinity will be, if it's very long, the salinity will be concentrated in such a way that the salinity will control the density field. And in that case, it'll be hypersaline and inverse estuary. Now, if they're not very long, but just long, they can be hypersaline, again because of evaporation. And then they're going to be here, that they're hypersaline but not inverse. And then if they're short basins, like a short bay, like Mission Bay in San Diego, if you know where that is. Short basins are thermally driven, so they're going to be here, and the temperature field will determine the density field, and those will behave as regular estuaries. So again, in those systems next to a upwelling coast, you're going to have a wide variety of systems located along this area where the temperature gradient is positive, that is, the temperature inside the basin is always warmer than the ocean because of upwelling. Upwelling cools down the temperature outside the basin. So given that, I mean, we've looked at maybe Chile, maybe southwest coast of the U.S., or the southwest coast of the U.S. What other coasts in the world do you have? Do you have where you have upwelling and embayments that might be showing this type of behavior? Where else do we have upwelling in the world? Right, Peru. That's a good candidate, actually. Just because it's dry, so the waters inside can be warmer and a hypersaline. But also in South Africa, where you have upwelling, South Africa, and also Northwest Africa, that's an upwelling region. And off Portugal, maybe too. All right, so those are areas where you could have these types of systems. And also for different thermal settings, you'll have these ones that we've talked about, that the water outside the basin is cold, so you have a positive thermal gradient. They're all hyperthermal. The temperature inside the basin or inside the estuary is greater than the temperature outside on the ocean. So these are along upwelling summer coast. And then you have estuaries and bays along tropical coasts where the temperature gradient is practically zero. There's no temperature difference between the basin and the ocean. And yet you could have sometimes where it's hypersaline, and in that case it'll be inverse, or hyposaline. In that case it'll be a classical estuary. So these are typically along tropical coasts. Can you explain why that is? Or think of an example where this could be happening? Think of an embayment in a tropical region that could show hypersaline conditions or hyposaline conditions.
India.
Yeah, good. So does it make sense that there's no temperature gradient between the basin and the ocean? That's provided that there's enough flushing, right? Because otherwise it'll become warmer. But in tropical regions, it's possible for that. So yes, in India or in Central America or in any tropical region that you can think of in the world, in Africa, you have systems that can either be inverse estuaries or regular estuaries, or that they can switch depending on the time of the year. I'll show you an example of a tropical system in Central America that shows a switch. And also in the high latitudes, where you have a hypothermal, that is, they're cold embayments, they can become hypersaline because of freezing, or they can become hyposaline in polar regions when you have a strong freshwater discharge. But still, the temperature of the basin will be colder than the temperature outside the basin. Okay? And if you add different hydrological settings, then in addition to the three that we've talked about before, in upwelling coast, in tropical coast, and in polar coast, this EBC means eastern boundary currents, but in winter only. Then you have, in dry climates and small watershed, you're going to have hypersaline conditions and inverse estuary. And in wet climates and large watersheds, like the Amazon, you're going to have a regular classical estuary. Or a large river in India, what would it be?
Ganga.
Which?
The Ganges.
So, but you said what?
I gave it a different name.
The first time is, the first time you said it.
Ganga.
Ganga?
Yeah.
Yeah, so you only knew what that one was. Only you knew what you say Ganges, maybe.
Yeah.
for us. Okay, so you have that situation too. So you can think that throughout the world you have, and these are just few of them as identified by last year. But as you have identified in Peru and Chile, you have also in Brazil and Argentina over here. Well, you can see all the areas of the world where you can have these types of systems. Low inflow estuary, where the river discharge is weak, or where the river discharge could be large, but only some times of the year. Some other times of the year, these systems might become hypersaline. So the larger basins are more persistent in their behavior, like in marginal seas and Gulf. In the Red Sea and the Persian Gulf, what do you think happens there in the Red Sea and the Persian Gulf? Right here. So you see. So those could be regarded as estuaries, but not estuaries. Why not classical estuary? What's the weather like, or the climate in that part of the world? Dry and hot, or dry and cold. So what do you think happens to the salinity in those basins? They behave very similarly, both in terms of the water balance in the basins. What do you think happens to the salinity? Right, they become hypersaline. So they are like inverse estuaries, and they're like inverse estuaries most of the year or all of the year. So they're more persistent. But most of these red dots that you see, and many others that are not included here as red dots, are smaller systems that can be seasonal. They can change their behavior from one season to the other, like these examples that I'm showing. Showing you two examples of systems that can show from classical to inverse, from one time of the year to another. So this is one in the Gulf of California, on the mainland side of Mexico. I think I've used this example before. Yeah, I've used it to illustrate wind-driven circulation. So right here we're looking at a transect at the mouth of this embayment. There's a bathymetry there. This channel is around 13 meters deep, and elsewhere the depth is very shallow. Mean depth in the whole basin is 2 meters. So you can see that the climate in this area is also very dry. So there's a lot of evaporation starting in March and going through October, November. Very strong evaporation, up to 3 meters per year, net evaporation. So in a small basin like this, what do you expect the salinity to do? Or what will happen to the salinity? It will become hypersaline. But then in the winter, something else happens. So here we have, in the upper panel, we have the situation during the summer. You see there, June. We're looking into the basin. There's the bathymetry, the depth. And you have water going in at the surface and coming out at depth. That's the time of the year when this system behaves like an inverse estuary. Inflow at the surface, outflow at depth. And then in the winter, February, you can see that you have inflow in the bottom and outflow at the surface. So like a classical estuary. But in this case, it's not because of buoyancy. In this case, it's because of wind-driven flow. During the winter, the winds blow from the northwest, so exactly along the main axis of this part of the bay. So those winds drive water out at the surface and a return flow underneath. Remember why we have this return flow underneath? No? Sorry? Right, the pressure gradient set up by the wind. The wind drives water away, sets up a slope, and that slope drives the water underneath. Surface slope. Alright, so this is an estuary that changes its behavior with the time of the year. Now think of this situation. there's a a fish processing plant right here. Can you see where? Right here. So there's one time of the year when this bay is smelly and you can see the pollution on the surface. And the other time of the year, it's still polluted, but it's not smelly, and you don't see the pollution on the surface, the pollution from the fish plant at least. So when do you think you'll have the smelly condition?
In the summer.
In the summer, that's right. Why is that? Yeah, because it's in at the surface, and it stays there, right? You lose water. That's why I was saying that you lose water, so those pollutants entering at the surface will stay there longer than if they were flushed, as in this situation, flushed away, flushed out. So this has not only interesting implications for the physics, but also implications for the water quality of the basin. So knowing what we know now, it's very silly to build a fish processing plant right there outside, right? So that's something that you have to take into account. Another example, and this is in Central America on the Pacific side. Let's see the geography now. What countries can you identify in Central America there? You know this country here? Colombia, very good. How about that one? Mexico, yeah. Okay, so let's go to the more challenging. How about that one? The neighbor to the south of Mexico. Guatemala, right? And then, well, Belize is right there also, just next to Guatemala, north a little bit. But, okay, so how about that one? Just south of Guatemala on the Pacific side. Sorry? No, Ecuador is further down. El Salvador. Oh, he knows his geography. Then, just north of El Salvador and to the east, north and east of El Salvador, you have it right here. Then Nicaragua, right here, and then Costa Rica and Panama. Okay. So after that, Central America geography lesson. We come back to the Pacific, and we have this very nice estuary. It's big. It's like 40 kilometers across here. So it's almost like 40 kilometers in this direction. But you see that those waters are shared by these three countries. And you've heard about these three countries, that they're a little belligerent, at least among themselves, inside and among themselves too. So working in those waters was a very challenging proposition. But anyway, I'm showing you data from this transect, and we're sitting inside the basin looking seaward in these two situations. So during the wet period, you have outflow at the surface, so outflow on this side. We didn't catch the mean outflow, which was around this area. So this outflow is outflow through here, and then inflow at depth there. Then during the dry period, you have inflow at the surface and outflow at depth. So the outflow is at depth and also leaning towards this area. This is the outflow and inflow. So this is an inverse S-train condition and a classical condition. And again, you could see differences in water quality. The basin is much bigger, but the differences in water quality were seen in these tributaries up here. And also in the soil. The soil gets very salty during the dry period. It gets hypersaline, the soil gets salty, and that salinity is also affecting the agricultural fields nearby. So that's something to consider too. What else? There's another important point here. Oh yes, that still, even though during the dry season you get some fresh water coming in from two rivers here. So if you have, it's a small amount, like 10 cubic meters per second. versus close to 150 or 200 during the regular season, during the wet season. So you have a small river discharge there. So if you have a small river discharge there, you're going to have low salinity somewhere here. But you have, and again, you have relatively low salinity here during the dry period. So say you have a salinity of 34 here, and maybe 12, 13 here, and 35 or 36 somewhere inside. So somewhere inside where you have the salinity of 36, you have what's called a salt plug. That's a region where you have strong convergence. So this fresh water cannot go out. And this relatively low salinity water still is a salinity of 34, so it's not very low salinity. While it tries to get in, remember you have inflow at the surface. While it tries to get in, it gets plugged by that salt plug. So you have, in that salt plug area, it's like a barrier. So those salt plugs are very deleterious for the water quality of the system because it's like a barrier that doesn't allow communication of the river waters with the ocean waters. And actually we want to study one of these in Rookery Bay, the area of the Thousand Islands, southwest Florida, where it becomes very hypersaline. And we think that that would be a good area to find these salt plugs, because you still have some fresh water coming into the systems, but you have hypersalinity in the system. So we're going to see how that affects also the suspended sediments, the turbidity maximum of the estuary. Anyway, so these transitions have very important implications for water quality and for soil quality, as you can see. And I mentioned this climate variability because this is what happens at oceanic scales. At oceanic scales, the Atlantic, the North Atlantic, behaves like an inverse estuary because you have water sinking in the North Atlantic right around Greenland and Norway because of the cooling, atmospheric cooling. Water gets cold and sinks, and that water gets all the way down to Antarctica. So that's sort of an inverse estuarine circulation. That triggers a basin-wide circulation that we can talk about in physical oceanography if you take it. But anyway, that's basin, global type of circulation that you can sort of scale it down to these types of to these systems. So by knowing how fast the transitions occur from an inverse to a regular estuary, we might be able to extrapolate to a basin-wide circulation and what's going to happen if we continue to warm and the North Atlantic water formation stops. So that's climate variability. Yeah, we could discuss this a long time if you had taken physical oceanography, but I won't do that. We can do it if you want at the end. So any given system, the main point here is that any given system can move around this diagram as you see here. So say if it's behaving like an inverse estuary in the winter, and you have a rain event in the spring, or maybe this could be in the summer, and then you have a hurricane that brings a lot of fresh water, then the inverse estuary will switch to a regular estuary. So this particular example from General Joyce from an upwelling, a system that's next to an upwelling center. And that's why this rain event occurs during the winter. So that's where most of the rain, say in San Diego, in Southern California, that's where you get most of your rain in the winter. So again, the rain event will push the estuary from an inverse to a regular one. And then as the water gets warmer, it'll go from a hypothermal to a hyperthermal, but also evaporation will start taking into, it will start influencing the density field. And in the summer, you're going to have here a thermal estuary that will be hypersaline but not inverse. And at some point, where the temperature difference is not that large, then it'll switch back here. So the two crucial points for the life of this system is this transition from inverse to classical and from classical to inverse. So these two are called the Stommel transitions because they were first described, these changes of regime from a regular to an inverse were first described by Stommel back in the 50s. And these are all theoretical developments, and there are frankly few examples of these Stommel transitions, observational examples. They've done them, they've been able to reproduce them in the lab, but in reality, we have very few examples. So that's a challenge for us to go and find examples of these and answer the questions: how quickly do these take place, and how persistent are they? These transitions. So can we detect Stommel transitions in Florida's lagoons and estuaries? That's a challenge. What is the temporal scale of the transitions? If we answer this question, we might be able to answer the question of climate change, the effects of climate change, with a little leap of faith, because we would be extrapolating findings from estuaries to the global ocean. But we might be able to do it. Now, what happens to the site fluctuation to the lagoons when you have these transitions, when the system transitions from regular estuary to an inverse estuary? Will agriculture be affected? Will tourism be affected? How would tourism be affected by these transitions, you think? Maybe causing droughts or salty conditions for the drinking water. So these areas become more vulnerable to droughts when you have this transition that become hypersaline. And also we need to study the implications on water quality and soil quality. Here's some food for thought, because we might be having them here, but we just not studying them carefully. So what's this area? Yeah. You don't see the, yeah. St. Augustine Inlet. So I'm going to show you data that compares temperature and salinity among these three different points. So here you have salinity for the entire year of 2004 at 4 Matanzas in red. That's a red line, as shown here, and San Sebastian right here. So at these 2 points, 4 Matanzas in red and San Sebastian in blue. And this is the temperature for the entire year also. So what do we see? Notice that the red line, which is 4 Matanzas, shows high salinity most of the time. So you have most high salinity, actually hypersaline conditions here relative to here most of the time. But what happens when the salinity goes down? What do you think caused these low salinity pulses? Notice that they were in around August. The hurricanes. Back in 2004, you were here already, right? Were you here when the hurricane? This was right before you started graduate. All right, so, and you had 3, right? 1, 2, and 3 right there. 1, 2, and 3. So notice though that 4 Matanzas is saltier here before these freshwater pulses, and during the freshwater pulses, 4 Matanzas gets fresher, so the situation gets reversed. So you might have a transition here, and then by this time of the year, do you see the arrow? I don't see it here. By this time of the year, then it goes back to 4 Matanzas being saltier. So as you can see from the chart here, most of the time this point is saltier than this point, but when you have a large freshwater input, I think because the freshwater comes from here, it's from Palisade Creek. Is that Palisade Creek? Do you know? Well, it's one of them. So most of the freshwater comes from here and here. So the salinity will be lower here than here when you have these pulses. So at those points you might have these transitions. Now we can talk about Stommel transitions here if and only if the mean flow through the the mean exchange flow through the inlet is driven by density gradient. And that's a big if. We don't know if that's true. Under these circumstances, it's possible that the exchange flow is driven by density gradient, because the density gradients might be large enough to overcome the tidal residuals, which typically are the ones that drive the mean flow in this inlet. Okay. Now, here for the same year, it's Pine Island is the red line, so up here, and San Sebastian is the blue line. Again, we're comparing this point to that point. That point to that point. So you see here that Pine Island salinity is lower most of the time, except here it becomes hypersaline, and maybe here, but those were the only 2 times during the year when the gradient, the horizontal gradient in salinity reversed. We will have to see whether the temperature compensated for that salinity gradient or it reinforced the density gradient. So that's a question to address. Now the following year, in 2005, again we're comparing Fort Matanzas in red line and San Sebastian, the blue line. So again you can see that Fort Matanzas for the most part is saltier than San Sebastian, except when with this pulse of low salinity water when Fort Matanzas became fresher. But notice here, in this particular one, it didn't become fresher, nor here. So this was also a tropical storm early in the season, back in 2005, in early June. Right, and for the same year, 2005, San Sebastian, which is the blue line, and Pine Island, which is the red line. You again see that Pine Island, for the most part, is fresher than San Sebastian, except maybe here, although it becomes the same. So it remains to see whether these reversals in salinity gradients are also consistent with reversals in density gradient, and those reversals in density gradient are driving any type of changes in the circulation, in the net circulation in the system. So these are questions that are, I think, in my view, very important to answer in order to address water quality and soil quality issues in systems like this. And we have them all around Florida. Other than the true estuaries where you have a lot of fresh water coming in throughout the year, like Tampa Bay and what others? Well, maybe St. Andrew. But think of all the other basins around the state that might be showing this type of behavior. So it's an area open for research. All right. Any questions or comments? But you can't change your topic at this point, right?